What if I told you that the moment you land on Jupiter, you would already be dead? No surface, no escape, and a storm so powerful, it has been raging for over 300 years. Today we're going to find out exactly what would happen if you tried to land on Jupiter. Jupiter is the largest planet in our solar system. It's so big that more than 1,300 Earths could fit inside it. But here's the problem. Jupiter isn't like Earth. It doesn't have a solid surface you can stand on. It's a giant ball of gas, mostly hydrogen and helium, with crushing pressure, deadly radiation, and unimaginable storms. So what happens if you go there anyway? Let's begin your journey. Before you even think about landing, you have to get there. And getting to Jupiter is itself an ordeal that tests the limits of human engineering. Jupiter sits roughly 628 million kilometers from Earth at its closest approach, a distance so vast that even light takes about 35 minutes to cover it. Your spacecraft, traveling at the speeds achievable by our best current technology, would take somewhere between 6 months and 2 years to make the journey, depending on the trajectory. As you draw closer, the first thing that would strike you, even before you entered the Jovian system, is the radiation. Jupiter is surrounded by the most intense radiation belts in the solar system, far more powerful than Earth's Van Allen belts. These are regions of space where charged particles, mostly electrons and protons, have been trapped and accelerated by Jupiter's immense magnetic field, which is about 20,000 times stronger than Earth's. Passing through these belts without adequate shielding would expose a human to lethal doses of radiation within hours. The Juno spacecraft, one of our most advanced probes, is equipped with a radiation-hardened vault just to protect its electronics. And even that takes a beating every time it swoops close to the planet. Assuming you survive the radiation, perhaps through some futuristic shielding technology, you would eventually find yourself approaching Jupiter itself. From orbit, the view would be staggering. The planet is a vast, swirling tapestry of amber, orange, cream, and brown, streaked with bands of clouds that wrap around the entire globe like the rings of a cosmic tree. Enormous storm systems, some larger than continents, churn and spiral across the surface. The Great Red Spot, that legendary storm that has persisted for at least 350 years and possibly much longer, glows like a deep crimson eye staring up at you from the southern hemisphere. You would also notice the moons. Jupiter has 95 known moons, and the 4 largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610 and still bear his legacy. Io, the closest of the 4, is the most volcanically active body in the entire solar system. Its surface covered in sulfurous plains and erupting volcanoes that fling material hundreds of kilometers into space. Europa, smooth and icy, hides a global saltwater ocean beneath its surface and is considered one of the most promising places to look for extraterrestrial life. These moons form a miniature solar system of their own, and as you orbit Jupiter preparing for your descent, they wheel around you like a slow, majestic clockwork. But you are not here for the moons. You are here for the planet. Here is the first and most important thing you need to understand about landing on Jupiter. There is no surface to land on, not in any conventional sense. Jupiter is what astronomers call a gas giant, meaning that the vast majority of the planet is composed of gas, primarily hydrogen and helium, rather than solid rock. There is no ground to touch down on, no soil to dig, no bedrock beneath your feet. What you are descending into is a planet-sized ocean of increasingly dense, increasingly exotic atmosphere that grows stranger and more hostile the deeper you go. Your descent begins as you breach the outermost layers of the Jovian atmosphere. At this altitude, roughly 1,000 kilometers above what scientists somewhat arbitrarily define as the surface, a reference point where atmospheric pressure equals 1 bar, equivalent to sea level pressure on Earth, the atmosphere is thin and cold. Temperatures here hover around minus 145 degrees Celsius. The sky, such as it is, glows with an eerie luminescence from Jupiter's intense aurora, far more spectacular than anything Earth produces. Great curtains of light ripple and dance across the polar regions as charged particles pour down the magnetic field lines. Almost immediately, you would encounter wind. And not the wind you are used to. Jupiter's upper atmosphere is dominated by jet streams, bands of wind moving in alternating directions that correspond to those iconic light and dark stripes visible from space. Wind speeds in these jet streams can reach 540 kilometers per hour, roughly 5 times stronger than a Category 5 hurricane on Earth. These winds are not occasional gusts. They are permanent, planet-encircling features that have persisted for as long as we have been observing them. Your descent vehicle would be buffeted ferociously from the moment it entered the atmosphere. As you descend through the upper cloud layers, the temperature begins to rise. You pass through layers of ammonia ice crystals. These form the bright, white uppermost clouds visible from space. Below that lies a layer of ammonium hydrosulfide, a compound that smells somewhere between rotten eggs and cat urine, forming reddish-brown clouds that give Jupiter's bands their distinctive color. Deeper still, you enter a layer of water vapor and water ice, more reminiscent of Earth's clouds, but swirling in the alien context of a hydrogen-dominated atmosphere. The Galileo atmospheric probe, dropped into Jupiter in 1995, transmitted data for about 58 minutes before it was crushed and vaporized. In that time, it descended roughly 200 kilometers below the cloud tops and experienced pressures of about 23 bars, 23 times Earth's atmospheric pressure at sea level. It recorded violent downdrafts, lightning, and unexpectedly high temperatures. It found that the winds were not slowing down as it descended, but actually getting stronger. This was deeply surprising and still not fully understood. Jupiter's weather is not solar-powered the way Earth's is. Much of the energy driving Jupiter's storms comes from the planet's own internal heat, a residual warmth from its formation billions of years ago. If you could somehow survive the winds, the cold, and the increasing pressure of the upper atmosphere, the journey would only become more surreal as you descended further. At about 100 kilometers below the visible cloud tops, you cross the 1-bar level, the notional surface. Here the pressure is what we breathe on Earth, but everything else is alien. The temperature has risen to a more manageable level, around 0 degrees Celsius in some regions. But the atmosphere is almost entirely hydrogen and helium, with no oxygen to breathe. You would be wearing a pressure suit with a self-contained breathing system regardless. But the reminder that even the air around you is fundamentally hostile is a stark one. As you continue your descent, the pressure climbs steadily. At 10 bars, the equivalent of diving 90 meters underwater on Earth, you are still in the upper reaches of Jupiter's atmosphere. At 100 bars, you are already deeper than any submarine has ever gone in Earth's oceans. And you are nowhere near the interesting parts yet. Around the 2,000-kilometer mark below the cloud tops, something extraordinary begins to happen. The pressure has climbed to millions of times Earth's atmospheric pressure. The temperature has risen to tens of thousands of degrees, hotter than the surface of the sun. Under these extreme conditions, hydrogen, the simplest and most common element in the universe, normally a light gas composed of 2 atoms bonded together, begins to behave in ways that seem to violate common sense. First, the hydrogen becomes a liquid, not because it has cooled down, but because the pressure is so immense that the molecules are forced into a liquid state despite the scorching temperature. You are now falling through a planet-sized ocean of liquid hydrogen. There is no sharp boundary between the gas above and this liquid below. The transition is gradual, a continuous thickening and compressing, until you realize that the material around you no longer flows like air, but moves with the viscosity of a fluid. And then, deeper still, perhaps 25,000 kilometers below the cloud tops, something even stranger occurs. pressure climbs to millions of atmospheres. At these pressures, the electrons in hydrogen atoms are stripped from their nuclei and flow freely through the liquid, the way electrons flow through a metal. The hydrogen has become metallic. Metallic hydrogen. This is not a theoretical curiosity. It is one of the most exotic forms of matter in the known universe, and it exists in vast quantities inside Jupiter. We have created tiny amounts of metallic hydrogen in laboratory settings for fractions of a second using powerful lasers and diamond anvil presses. But inside Jupiter, it exists in a layer thousands of kilometers thick, conducting electricity and swirling in great convective currents. It is these currents of metallic hydrogen, this deep, roiling, electrically conductive ocean, that generate Jupiter's extraordinary magnetic field. The movement of conducting fluid creates a dynamo effect, just as Earth's liquid iron outer core generates our much weaker magnetic field. Jupiter's magnetic field is not just a scientific curiosity. It is a force of nature powerful enough to trap enough radiation to kill an unshielded human in minutes. And it extends millions of kilometers into space, dominating a region far larger than the Sun itself. At the very heart of Jupiter, beneath the metallic hydrogen ocean, lies what scientists believe to be a core. But what exactly that core is made of remains one of the great open questions in planetary science. For a long time, the prevailing model was that Jupiter has a dense, rocky core, perhaps 10 to 20 times the mass of Earth, composed of silicates and metals compressed to unimaginable densities. Recent data from the Juno spacecraft, however, has complicated this picture significantly. The gravitational data Juno has sent back suggests that Jupiter's core may be much larger and less distinct than we thought. A fuzzy core that blends gradually into the metallic hydrogen surrounding it, extending perhaps halfway to the surface. Some researchers now think that Jupiter may have experienced a giant impact early in its history, a collision with a young protoplanet that could have stirred and diluted the core, smearing it into the surrounding layers. If you could somehow reach the core, traveling some 70,000 kilometers from the cloud tops, you would be in a region of pressure estimated at 40 to 60 million times Earth's atmospheric pressure, at temperatures of perhaps 35,000 to 40,000 degrees Celsius. The material around you would be compressed to densities many times that of any substance you have ever encountered. At these conditions, matter itself behaves in ways our physics struggles to fully model. The distinction between solid and liquid loses much of its meaning. Rock and metal, if they exist down here, would be compressed into states that bear no resemblance to their familiar forms. You would not be alive to see it. You would have been crushed, vaporized, atomized, and reintegrated into the ambient material of the planet long before you got anywhere near the core. But intellectually, knowing it is there, that vast, mysterious heart at the center of the solar system's largest world, is extraordinary to contemplate. This thought experiment is not merely an exercise in imagining human death in creative ways. It points toward one of the most important frontiers in planetary science and our understanding of the cosmos. Jupiter is not just the largest planet in our solar system. It is in many ways the most important. Its enormous gravity has shaped the architecture of the entire solar system, deflecting asteroids, influencing the orbits of other planets, and acting as a kind of cosmic shield that may have protected the inner solar system, including Earth, from a much higher frequency of large impacts. The question of whether Jupiter's presence was essential to the development of life on Earth is a serious one that researchers continue to debate. Understanding Jupiter's interior, particularly the behavior of metallic hydrogen, has implications far beyond our solar system. Most of the planets discovered around other stars are gas giants, many of them far larger than Jupiter, orbiting much closer to their stars. To understand these worlds, we need to understand Jupiter first. The physics of metallic hydrogen is also relevant to fusion energy research, stellar astrophysics, and our fundamental understanding of how matter behaves under extreme conditions. Future missions to Jupiter, including more sophisticated atmospheric probes and potentially long-duration orbiters, will help us peer deeper into the planet's secrets. Scientists dream of a probe that could survive long enough to descend below the cloud layers and send back data from the strange, pressurized depths. Though building anything robust enough to survive even briefly at the tens of bars level is an enormous engineering challenge. So what happens if you land on Jupiter? You descend through hurricane-force winds and poisonous clouds. You pass through layers of ammonia and sulfur and water. You enter a liquid hydrogen ocean under crushing pressure. You are compressed by forces beyond anything in human experience, heated to temperatures that dwarf the surface of the sun, and ultimately dissolved into the same primordial hydrogen and helium that has made up this giant world since the earliest days of the solar system. You do not survive. No version of this story ends with a human being planting a flag and looking around. But that is precisely what makes Jupiter so magnificent. It is a world that does not care about human ambition or human fragility. It exists on a scale and operates by rules that lie entirely outside our everyday experience. It is a reminder that the universe is not scaled to us, that most of it is violent and extreme and profoundly indifferent to biology. And yet here we are, a small species on a small planet, using mathematics and spacecraft and imagination to peer into the crushing depths of a world that would kill us instantly, and learning something true about the nature of reality in the process. That is the real miracle. Not that we could land on Jupiter, but that we can understand it. That the human mind, built for the savannas of Africa, for tracking prey and reading weather, turns out to be capable of modeling the behavior of metallic hydrogen at 40 million atmospheres of pressure. That we can look at a swirling storm larger than our entire world and work out what is driving it. Jupiter will never welcome us, but it has a great deal to teach us. And from a safe distance, in the cold dark between the planets, it is one of the most beautiful things in the sky.